Okay, now we're going to do something called differentials. And don't let the terms get you confused. And let's look at why differentials might be important to us. Let's do an approximation. Let's approximate the tangent line through this curve at the point 0, 1. So at that point right there, let's see if we can figure out what the slope is. And let's find the first derivative of x. That's 2 cosine of x. So now we can evaluate f prime at the point x equals 0. So the slope at 0 is 2. Now we know the tangent line at a point can be written y minus y naught is the slope times x minus x naught. Now in this case, x naught is 0, and this is f evaluated at x naught. So that's our point. So if f prime is 0 is 2, let me come over here and find out what is f at 0. All right, and we see that that is just 1 plus 2 sine of 0 is just 1. All right, so let's write a line, equation for the line. My line is going to be y minus this y naught, which is right here. Y minus 1 is equal to my slope, which I found to be 2, times x minus 0. So I can write my equation as 2x plus 1. Well, we can do this. That was quite a bit of work. Let me show you. Hold on. First of all, I want you to do one. Pause the video. When you're done, come back because we got more to do. All right. Now, let's define differentials. Write this definition down. Let y equals f of x represent a function that's differentiable on an open interval. So here's my function. All right, the differential of x, denoted by dx, is any non-zero real number, and the differential of y, denoted by dy, is given by. Now dy, okay, if I do dy by dx, I know that that is f prime of x at any point. All right. So the slope at any point then is its derivative. And if I break this up, now I'm going to be a little fast and loose here with the algebra skills. We're not actually multiplying across. But I can say that the differential of y, or dy, is the slope at any point times the differential of x at that point. All right, let's see what this means and why we would use it, and goodness gracious, let me thin my line down here. Let me let y equal x cubed. And let's find dy when x is 1, 0.01, when x is 1 and dx is 0.1, 0.01, and 0.001. All right, the first thing I'm going to do is, let's see, f of x is y, which is x cubed. So the first thing we need to do is find the derivative. So the first derivative of x, which is going to be 3x squared. All right, now I know my differential in y is f prime evaluated at x at any point times dx. All right, now let's let dx equal 0.1. Let's start with the first one. Dx is 0.1. F prime at, let's see, x is 1 as well. f prime at 1, what's the derivative of evaluated at 1 is just 3. All right, so f prime at 1 is 3. So dy is f prime evaluated at 1 times the differential of x. So it's going to be 3 times 0.1 or 0.3. Now let me do it when dx is 0.01. Then dy becomes 3 times 0.01 or 0.03. And what about when dx is 0.001? Well, then dy is 3 times 0.001, which is 0.003. All right. So you can see as the differential in x decreases, the differential in y also decreases. Well, that's finding dy. What if I were to go through and find delta y? Let me switch colors here. All right, now I'm going to compare delta y. And I think you're going to see something kind of interesting. Delta y, I'm going to do right here, if I can get my pen to work, is equal to f of x plus delta x minus f evaluated at x. So what I'm going to do is let me figure out, let's see, f of 1 is 1 cubed, it's just 1. Okay, so that's pretty easy. So now let me go through and see if I can find my delta y with each of these delta x's. All right, so instead of dx, I'm going to use these, the differentials are going to become the changes in x. So when I let delta x equal 0.1, delta y is, now the function at x plus delta x is going to be 1.1 cubed minus 1. And it turns out that that is 1.331 minus 1, or 0.331. Oh, that's actually pretty close, isn't it? I mean, it's off in the hundredths place. What about when delta x is 0.01? Then delta y is 1.01 cubed minus 1, which is 1.0303 minus 1, or 0.0303. Well, this one's actually quite a bit closer to my differential there. What about when delta x is 0.001? Then delta y is 1.001 cubed minus 1. And this now is 1.00300. Oh my gosh. So this one is in very close agreement. So we see that as the delta x, the limit as delta x goes to 0, we begin approximating our differential. Starting to hear a little calculus shoved in there? Okay, give this a go. Stop the video and restart it. When you're done, we're going to do an exciting problem. All right. Okay, I think it's exciting. We're going to do error propagations, and I'm going to do this in red because we know all errors are done in red. Suppose that I measure something. It can be the length of a tube or the diameter of a ball bearing, and you're going to do this in physics. You're going to have to measure a ball bearing with some measure of accuracy. Let's let x equal your measured value, but it's not precise or it's not exact. So we're going to let x plus delta x be your exact value. That tells me that delta x is your error in measurement. Delta x can be positive, it can be negative. And your propagated error, delta y, is going to equal f evaluated at x plus delta x. So it measured at the exact value minus your measured value. Now, propagation of error is pretty significant, folks. I did an experiment when I was working at Argonne National Labs where I had to solder down 10 micron wires 1 millimeter apart. And I got off because I started measuring off of the different wires. And, oh, it wasn't very good. Okay, let's look at this problem right here. I have the radius of a ball bearing is measured to be 0.7 inches. Now, it's measured to be 0.7, so I'm going to let my radius equal 0.7 inches. If the measurement is correct to within 0.01 inch, so that tells me that my delta R is between negative 0.01 and positive 0.01. They estimate the propagated error in the volume of the ball bearing. All right. Well, volume of a sphere is 4/3 pi r cubed. All right. So if I do dv dr, what do I get? This becomes 4 pi r squared. All right. Now I'm going to approximate delta v with dv. All right, so this is dv. I'm going to solve this for dv. It's 4 pi r squared dr. Now, my r is between 0.01 and negative 0.01 and 0.01. So I'm going to put my values in here. So this is 4 pi. R is 0.7 squared, and this dr is plus or minus 0.01. So when I multiply this out, I get my volume is plus or minus 0.06158. Now is this good or bad? Well, the answer is depends upon what the original volume was. Let's look at dV divided by the actual volume. All right, dV is 4 pi r squared dr. We just did this. And then the volume itself is, of course, 4/3 pi r cubed. Now, you could have done this separately and assembled them later, but we didn't. So this is 3 dr divided by r. So let me plug my numbers in. So this is 3. Now dr is plus or minus 0.01 and divided by my radius, which is 0.7. So I get this is plus or minus 0.0429. This corresponds to 4.29% error. So is this a good estimate or not? Well, it depends. If you need an error under 5%, it's great. If you need error under 2%, not so great. Okay, you give it a go. And when you're done, turn off the video and finish your homework.